Hello, class. The last portion of this chapter, we're going to cover conservation of momentum. We can observe conservation of momentum in action through all collisions. There are two types of collisions we'll discuss in this course. The first type is elastic collision, where two objects bounce off each other. And the second type is inelastic collision, where two objects bend during the collision or stick together. The first example below shows two objects in an elastic collision. The definition of conservation of momentum is the net momentum before the collision must equal the net momentum after the collision. The apostrophe represents final velocity of the object. So the object A and B elastically collide into each other, and the final velocities are pointing in the opposite direction, and their final speed would depend on the mass of object A and B and their initial speed. If we were to analyze the conservation of momentum for a rocket, we would also have to consider the loss of mass of the rocket's fuel. However, in this course, we're not going to go over the rocket equation. Here's our first example. We have a 10,000 kilogram railroad car, A, traveling at speed 24 meters per second, and it strikes an identical car, B, at rest. If the cars lock together as a result of the collision, what is their common speed just afterwards? First step is to start off with the conservation of momentum equation. The initial velocity of car B is 0, and the final velocity for car A and B are the same. So I just factored out the final velocity. Our equation reduces. Solve for final velocity. Plug and chug, and we get 12 meters per second. In our next example, we have to calculate the recoil velocity of a 5 kilogram rifle that shoots a .02 kilogram bullet at a speed of 620 meters per second. Again, we start with conservation of momentum equation. But in this example, both objects start from rest. So our equation reduces. Solve for the final velocity of the rifle. Plug and chug, and we get negative 2.5 meters per second. Notice the negative sign. This means that the rifle is recoiling backwards. During a collision, kinetic energy is conserved only for elastic collisions. This is because during inelastic collision, some energy is lost mainly to heat due to friction. Example C shows an example of an elastic collision, whereas example D shows an example of an inelastic collision. One difference you should notice is the final velocity is not the same between example C and D. Again, this is due to energy loss or is transformed into heat during the inelastic collision. In this course, we'll only deal with problems that are either elastic or completely inelastic. Completely inelastic just refers to two objects sticking together when they collide. Here's an example of what I mean by completely inelastic collision. Object 1, the bullet, has some initial velocity, and Object 2, the block, is at rest. When the bullet collides into the block, they stick together because the bullet is stuck in the block. What we can conclude from this scenario is that the final velocity of the block and the bullet is the same because they move together. So here's an example. The projectile of mass m is fired into a large block of wood, mass m, capital M, which is suspended like a pendulum, and as a result of the collision, the pendulum and the projectile are swung up to a maximum height of h. We want to determine the relationship between the initial horizontal speed of the projectile, v, and the maximum height, h. We start off with conservation of momentum. Now, I already factored out the final velocity since it's the same for both objects. The block starts from rest, so the VBI equals 0. And our equation reduces down a bit. However, we don't know the final velocity of both objects, but we do know their final height. So we can use conservation of energy to find the final velocity in the conservation momentum equation. Notice how this problem just turned into a two-part process. The initial potential energy and the final kinetic energy equals 0 because we take the reference point for potential energy at the bottom of the pendulum of the object, and the object comes to rest at the maximum height of h. Next, just plug the equations in for kinetic energy and potential energy. Look at that, the mass cancels out. And our equation reduces down. Solve for the initial velocity, which really is the final velocity for our conservation of momentum equation. So I'll just go ahead and change the subscript there. If we had numbers, we could solve for what the value is for final velocity. Then I'll go ahead and rearrange the conservation of momentum equation to solve for the initial velocity of the bullet, which is VAI. Since there are no numbers in this example, we're going to stop here. But if we knew the height and the mass of the objects, we could calculate the velocity of the bullet.